Good morning. Today's lecture we are going to spend a substantial amount of time on the all pass filters, and the reason all pass comes in is because we are now we have studied the looked at the option of eliminating phase distortion in a two channel filter bank, and we said let's go back and relook at the problem of eliminating magnitude distortion in a two channel filter bank. So just to quickly summarize the key results from the previous lecture, we are looking at the two channel filter bank. Add to this that it is a maximally decimated filter bank, it is a maximally decimated two channel filter bank, and also add to it the fact that we are using quadrature mirror filter property, so that we have to design only one filter from the entire discussion. So the two channel filter bank with the constraint that the QMF constraint H1 of Z is equal to H0 of minus Z. This is the QMF constraint. On top of that we have the aliasing cancellation constraints as well. So you can add to this the aliasing cancellation constraints. Then this collapses to a transfer function which we can work with. Now if you do the polyphase decomposition, this is the expression that we get, 2 times Z inverse E naught of Z squared E1 of Z squared. If it is not the polyphase decomposition, if let us say you are looking at the phased elimination part, we said we look at a type 2 linear phase filter, and the expression for the transfer function Te of j omega came out to be 1/2 e power minus j omega n h naught magnitude squared h1 magnitude squared, or h0 e power j omega minus pi magnitude squared. So basically the overall transfer function has got linear phase, magnitude phase distortion is eliminated, aliasing eliminated. We just had to deal with the magnitude distortion and make sure that is as close to a constant as possible, therefore we would get minimum magnitude distortion as well. We spent a bit of time looking at the design of a two channel filter bank, and we said that depending upon how we choose the stop band plays a very important role, and the stop band will more or less then decide where the crossover occurs, and then you may get when you plot the overall transfer function, as long as your stop band energy is small, you are going to be small in this region and also in this region. The only uncertainty is in the overlap where the transition band occurs, and that is what we tried to optimize in the discussion yesterday. So the stop band energy, so this is the expression for the stop band energy, that is what tells us that we will get a good low pass shape. The question that was asked yesterday is how does that alone guarantee that the pass band is good? That alone cannot guarantee the pass band is good. So actually the combination of the flat constraint, let us call this as the flatness constraint, the flatness constraint of Te of j omega. The combination of the flatness constraint and the stop band energy, we argued, actually gives us the constraint. Actually there is one error that was pointed out. What you have within this bracket, the square brackets, is a term that can go positive or negative. So actually you have to square it before you integrate, so that you get a positive quantity, and therefore it becomes a quantity that can be minimized. So make sure that the square is inserted. The objective function that we are going to is alpha times phi 3 minus 1 into 1 minus alpha times phi 2. So the problem statement, if I were to rewrite this, supposing you were to sort of say it afresh. So the two channel maximally decimated filter bank, maximally decimated QMF filter bank, okay, we have come to the stage of designing the filters. So we will apply the aliasing cancellation constraint, apply the QMF constraint, and then the two functions that we are specifying are phi 2, which is integral of omega s to pi, this is the stop band energy, h0 E of j omega magnitude squared d omega. Phi 3 is over the entire range from 0 to pi, 1 minus mod h naught E of j omega magnitude squared minus mod h naught E of j pi minus omega or omega minus pi, does not matter, whole squared, and this one whole squared. Okay. So, let me just change the color so that you will not miss that. So, there is a outer square times d omega, and the overall objective function is alpha times phi 3 plus 1 minus alpha times phi 2. We said we will call it as phi bar, that is the objective function, and the optimization problem now states that the optimization task is to find the coefficients of the filter h naught, h1 all the way to h of n plus 1 by 2. Keep in mind that we are designing a type 2 linear phase with even symmetry. So, that is why we need to worry about only half the coefficients, the other half will be the same in reverse order, and find these coefficients such that the objective function phi is minimized. So, actually is a numerical optimization problem that we will set. Okay. So, what are the design parameters? What can you vary or what do you have to specify? The design parameters are only two. Number one, it is the filter order n, that tells you how many coefficients are going to be optimized. The second design parameter that we have to specify is omega s, which is the stop band edge, because in your objective function that is the only one that is not yet specified, all the others then get specified, stop band edge. Okay. And implicitly once you fix the stop band edge and you have constraints, constraint phi 3 through phi 3 this, once you specify omega s, omega p gets fixed because of the flatness constraint that we have specified gets fixed. Okay. And interesting to observe the following, maybe you already sort of noted that if you sketch the h naught, it has a crossover around, okay, I should always show the ripples because these are not ideal filters. So, some ripple in the passband and then, okay, that is the, and if I draw the shifted version, it is going to look identical. Okay, because it is the original filter shifted. So, let us mark off the what has been specified. This is omega s. Okay. So, what is this? That will be pi minus omega s. Notice that because of the flatness constraint, these two will have to align, right, because that if that is the point at which the stop band of the red filter is starting, that should align with, otherwise the flatness constraint will not be satisfied. That edge where the green the passband edge of the green filter, that is omega p for the green filter. Okay. So, omega p has to line with pi minus omega s because of the symmetry constraints, or in other words omega s plus omega p are respect to pi. Okay. So, there is a constraint that omega p gets fixed without being actually being explicitly specified because of the symmetry constraint, the flatness constraint, and you can also look at it pictorially. Okay. Now, let us go back and re-look at the problem where you decided to use it as all pass filters. Take it, I am sorry, okay, you will have to specify, yes, of course, yeah, good point. So, maybe we add that as the third one. because you want to give a certain weightage, so you can add that as the, I should have mentioned that alpha is also something that you have to specify. Okay, now if you now look at the polyphase decomposition, okay, so the phase elimination part is done, the design of the filter bank is done. We will do a MATLAB exercise just to make sure that we actually can verify the flatness constraint. Okay, the next part where we were trying to eliminate the magnitude magnitude distortion. So, eliminate magnitude distortion. You are back to a problem that we have studied before, but hopefully with a little bit more insight that we can derive this time. Eliminate magnitude distortion, the polyphase components, the overall transfer function will be 2 times Z inverse E naught of Z squared E 1 of Z squared. The last time we forced them to be delays, it is not necessary, we said that they could be all pass filters, and if they are all pass filters then the transfer function comes out to be T of Z, Z inverse by 2, A naught of Z squared, A 1 of Z squared, A naught and A 1 are all pass functions. So, therefore, you get perfectly flat T of Z response, and all you need to now worry about is how do you get good filters, and in the process what has happened to the phase. Okay, so, that is the part at where we have stopped. We said that elliptic filters with certain constraints actually do satisfy this property. Let me just make a couple of statements about the elliptic filter, again encouraging you to read the following sections, PPV sections 5.1, 5.2, 5.3, 5.1, 5.2, 5.3. Those are the sections which we are covering today, and intuitively this is what is happening as far as the elliptic filter is concerned. Elliptic filters belong to a unique class of IIR filters which have a very distinct type of property. Both there are ripples in the passband, ripples in the stopband, and those ripples are equiripples. So, elliptic filters have got a very unique property. So, if you were to sketch an elliptic filter, you will see something of this type. Okay, I have sort of exaggerated the ripple, and you will see something of this type. Okay, so, there is a very interesting now typically when you design a filter, low pass filter, you specify this to be equal to 1 and your ripple goes on either side, and basically your upper point you call it as 1 plus delta 1, the lower point as 1 minus delta 1, and the total ripple as 2 times delta 1. Now, we are going to do something slightly different. We are going to normalize the peak value to be equal to 1. Okay, if you normalize the peak value to be equal to 1, then this point now becomes 1 minus 2 times delta 1. You kind of have normalized it. So, again the reason you are calling it 1 minus 2 delta 1 is evident from the convention. Usually it is 1 plus delta 1 and 1 minus delta 1, you have called this. So, if I were to plot the magnitude squared H naught E of j omega magnitude squared, okay, if I were to plot that, this would be squared. Okay. So, that is the, and so for the squared response, if I call this as delta, that is the total deviation for the squared response, what will this be? This typically would have been called delta 2. When you square it, it will become delta 2 squared, that is the stop band energy, and because of the elliptic filter property, and if we specify that this is also equal to delta. Okay, so, what you are trying to force your elliptic filter to have the following constraint, that your ripple for the squared response, the ripple in the pass band and the ripple in the stop band are the same. Again, these are design constraints that can be implemented. So, not restrictive in any way, we just want to make sure. Now, very soon it will, or in a minute you will see why we are trying to go through this exercise. But if you do satisfy this, so then the constraint that we have now imposed on the elliptic filter design is delta equal to 1 minus 2 delta 1 whole squared. 1 is the upper line, the lower line is 1 minus 2 delta 1 squared, the deviation is this is also equal to delta 2 squared. So, delta 1 delta 2 from the definitions, and we have done some scaling. So, therefore, this is the, and this is constraint number 1 for the elliptic filter. The second constraint is, again probably no surprise, omega p plus omega s equal to pi. Okay, omega p plus omega s equal to pi. Now, I force that constraint as well, and then a third constraint that will come about is T e of j omega equal to magnitude h naught e of j omega h naught e of j omega magnitude squared plus h1 e of j omega magnitude squared. Again, the QMF constraint says that this is actually h naught e of j omega minus pi or pi minus omega magnitude squared, that is the same, and this being equal to 1. Okay. Now, under these constraints, we are guaranteed that the polyphase decomposition of this elliptic filter will result in all pass functions. Okay. There is a fair amount of theory to prove that. Again, what we are going to do in our class is to actually assume that the all pass functions exist and then move forward, but for the complete picture, these are, and you can kind of get a feel for it. What we have said is there is going to be a quadrature symmetry. So, basically this point is going to be pi by 2. Okay. These ripples are of the same level. So, when I flip it and add them together, then there is a chance that where there is a dip, if I have a peak, then actually I will get a constant. So, again the way we have constrained the design or of the elliptic filter kind of says that, okay, this is something that was straightforward, this is something that is can be imposed. The tricky part was how do you get the complementary property. So, any pair of filters h naught and h1 that satisfy this kind of a property, that their magnitude squares add up to a constant, actually belong to a class of filters called the power symmetric pairs. Power symmetric pairs. So, h naught and h1 must come out to be a power symmetric pair because of the QMF condition. There is also sometimes this is also referred to as a power complementary property. A power complementary property. Okay, so the powers of h naught and h1 are complementary so that they can add up to a constant. So, power symmetric or power complementary property, these are all things that we are going to just sort of engage with, but just wanted to give you a heads up on what enables us to satisfy this. Okay. Now, given this set of conditions, the 1 and 2 are straightforward. Third is a property that we would have to be careful to deal with, but this class of power symmetric filters exist. So, given this, the elliptic filter designed with these constraints will be decomposable in the following way. So, given that statement, we will come back to this once we have studied all pass filters. Now, we are going to spend the next portion of the lecture and a bit, depending on again your familiarity with all pass, we will spend some amount of time. So, the first thing in our study of all pass functions, you can also call it all pass filters, but all pass functions or filters. By the way, this is also covered very nicely in Vaidyanathan's book, chapter 3. There is a section on all pass filters. Again, definitely would encourage you to read that. Okay, the first one I would like to introduce to you is notation. There is a lot of notation that is that may be somewhat new. I just want to introduce that so that you are comfortable with it. If I have a polynomial h of z, a plus b z inverse, where a and b can be complex. Okay. I am going to define the following h of z tilde as, I am going to define it in the following way. it is A conjugate plus B conjugate times Z. This is called para conjugation. Now, where does this come from? How do you get something like this? Maybe if you have not seen it before, does not look intuitive at all, and why do you have to give it a name, for example. So, now let us anchor para conjugation in terms of the operations that we are familiar with. Now, instead of H tilde, if I had asked you to do H conjugate of Z, okay, conjugate the function. So, anything that is a complex number on the has to be conjugated. So, if you do that, then what you get is A conjugate plus B conjugate. I am going to write Z inverse as 1 over Z. Z is a complex number, so therefore it is 1 over Z conjugate. So, this is conjugation. Okay, and yet another notation that is going to be introduced is when I have a polynomial with complex coefficients. If I put the conjugation side, that asterisk at the bottom, that says conjugate the coefficients, leave the Z terms alone, don't conjugate those. So, then what you get is A conjugate plus B conjugate Z inverse. Okay, so, this is coefficient conjugation, only coefficient conjugation. Okay, so, three things we have introduced. One is para conjugation, where you conjugate and change Z inverse to Z, conjugation of the expression where all terms including the Z term gets conjugated, and then you have the coefficient conjugation. Okay. So, now using these as the components, I would like you to just verify that H tilde of Z can be written in two ways. The first one is coefficient conjugation, only thing that does not change is Z, replace Z with Z inverse. Do the coefficient conjugation and replace Z with Z inverse, or if you are going to do the traditional conjugation where everything gets conjugated, then what we have to do is you will end up with 1 over Z star, do not want that, replace that with 1 over Z star, replace Z with 1 over Z star. So, basically 1 over Z will become it will become Z, and Z star star will become Z itself. So, basically you will get what you are looking for. Okay. So, there are two ways of expressing it. Again, this is just to make sure that you are comfortable with the notation that we have introduced. Now, here is the important part. H tilde of Z is called the para conjugate of H of Z, is called or is referred to or is defined as the para conjugate of H of Z. Okay, a lot of this comes from the theory of analytic functions and complex variables, and again you may have been exposed to it. I am using only that parts that I need for us. Okay. Now, why are we even defining the para conjugate? So, when you look at this function on the unit circle, so H of Z evaluated on the unit circle E of j omega, you can say that this is equal to A plus B E of minus j omega. Okay. Now, if I conjugate H conjugate E of j omega, then what do I get? I get A star plus B star E of j omega. Okay. Now, please evaluate H tilde of Z, Z equal to j omega, you actually get the same thing, you get A star plus B star E of j omega. Okay. So, the reason we have defined the para conjugate is because this is the analytic extension of conjugation on the unit circle. That is as simple as that. Z plane has a unit circle, conjugation is defined on the unit circle, everywhere else you have to define an analytic extension of conjugation, which is what. So, this is the analytic extension of conjugation of on the unit circle, extension of conjugation on the unit circle. Okay. Again, this is something that you would have studied as part of your analytic functions and properties. Even otherwise, Vaidyanathan's book gives an excellent overview of the those results that we need from complex variable theory. Okay, so one of the things that we are often interested in the design of filters, in our case, once we start trying to impose these magnitude constraints, is magnitude h e of j omega squared, and this can be written as h of z, h tilde of z, z e of j omega, because what basically the writing it mathematically, saying that something is the analytic extension of conjugation on the unit circle, sort of takes it to the next level by saying, instead of just writing h conjugate e of j omega, often we are interested in magnitude squared, which means it is product of h and h star. Everywhere else on the unit circle, other than the unit circle, you will have to represent it as h of z and h tilde of z. Okay. So that is a useful representation for us, and we would like to sort of keep that picture in mind. Now, why did we do this, and what are the benefits of this? A lot of the insights come in a very short time. Let's pick up from there. So focus now on all pass filters, and would like to sort of use a result right at the beginning, right off the bat. Now, if I have a of z as some polynomial, okay, a naught plus a1 z inverse dot 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 a n z power minus n, okay, a tilde of z is given by a naught conjugate a1 conjugate times z dot 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 plus a n conjugate z power n. Am I right? So this is non-causal. Okay, but if I do z power minus n times a tilde of z, then what do I get? Get a n star a n minus 1 star times z inverse dot 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 plus a naught star z minus n, which is causal. Okay. Now, here is the key result. Now, if I tell you, please look at a transfer function which is of the following form: a of z, z inverse a tilde of z, okay, and evaluated on the unit circle, z is equal to e of j omega. So this evaluated at z equal to e of j omega, this comes out to be e power minus j omega n. A tilde is nothing but a conjugate e of j omega, denominator is a e of j omega. Okay. Take the magnitude equal to 1. So this is the general form of an all pass filter. Okay. So the reason we have gone through this a tilde business and the analytic extension, all of that is just sort of, we get very compact expression, understanding of what the structure of an all pass filter is going to be, because now you can verify that magnitude h e of j omega equal to 1, and this is the basic property of all pass functions. So in other words, the transfer function h of z is a ratio of the analytic extension of basically it is some polynomial and its paraconjugate, ratio of the paraconjugate. Once you visualize it like that, and you know that on the unit circle these are conjugates of each other, then the all pass property falls into place. The beauty of it is it also tells us the structure of the system. So what do I mean by that? Where are the poles and zeros located? So let us take a very simple first order example. I am sorry, z power minus n, thank you, yes, z power minus n. Okay, first a very simple example. Okay, I want to look at a first order system. A of z is 1 minus a z inverse, okay. Z in for order is equal to 1, so I have to multiply the numerator by z inverse by times a tilde of z, 1 minus a conjugate times z, okay. Now tell me where the poles and zeros are located. I look at the denominator first. There is a pole at z equal to a, okay. If I can write it as modulus of a e power j theta. So I got a magnitude, and so if I were to sketch this, that is the unit circle. Modulus of a, if assuming that this is a stable all pass, so stable implies mod a has to be less than 1 and some angle theta. So again, just for argument's sake, if this is the angle theta, then well, maybe I should draw it the other side. Okay, if this is angle theta, that is the radius mod a. So this is where the pole is located, okay. Now go back and look at the 0. We find that there is a 0 at z is equal to 1 over a star, z equal to 1 over a star. So that will be equal to 1 over mod a times e of j theta. So it is along the same radial direction, but at a distance of 1 over a, 1 over mod a, okay. Now I am sure you are familiar with the in the sketching of poles and zeros. So if I have a complex pole located at a, this is a conjugate, this is 1 over a, and this is 1 over a conjugate, right. Those are the locations of the, so but that is how you would look at the poles and zeros. So yes, the wherever there is a pole, you will also have a 0 at the conjugate location, reciprocal conjugate location. That is what this says. And again in chapter 5 of Oppenheim and Schaefer, you would have looked at frequency response, right. How do you look at frequency response? Distance from the 0, distance from the pole, take the ratio of that. So basically when they are at reciprocal points, those distances, the ratio is always maintained. So therefore wherever you go on the unit circle, the ratio of the distances is maintained, and therefore you get a constant value. That is how an all pass function is structured. So the para-conjugation property actually gives us a lot of insight into saying that because of the para-conjugation relationship between the numerator and denominator of an all pass function, then we can say that all poles and zeros have to be located in this fashion. Only then the all pass function will be satisfied. Okay. So we are starting to get some interesting insights. Again, let us quickly move forward, because this is not our main goal. Our goal is to use all pass functions. So in the general case, Hn of z would be written as an nth order all pass would be written as b naught plus b1 z inverse dot 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 plus bn z power minus n. Numerator will be bn star plus bn minus 1 star. So the general form of all pass function, we write it in this form, and then now we would like to analyze this. So let us write down bn of z as the polynomial, summation n equal to 0 to uppercase n z power minus n b of n z power minus n, b of n z power minus n, and a n of z is the para-conjugate with the appropriate shift z power minus n b n tilde of z, okay, and that can be written as summation n is equal to 0 to n b of n minus n conjugate z power minus n. Okay. Now here is the argument that we make based on what we discussed for the earlier case. Because of the paraconjugate nature, we make the following statement: if h of hn of z, suppose hn of z is an nth order all pass, that is what we have constructed it to be, is an nth order all pass with a pole at z equal to alpha 1, okay, then it must have a 0 at 1 over alpha 1 conjugate, it must have, only then the all pass property will be satisfied. So, this also means that there is a hn of z has a 0 at 1 over alpha 1 star, it has to have, that is the structure of the all pass. So, this also can be combined to make the following statement, that if I pull out this particular pole and this particular 0, then hn of z has a factor of the form 1 minus alpha 1 z inverse, that is the pole minus alpha 1 conjugate plus z inverse, that is the 0, there is a factor of this type. Very, very important. This means that an nth order all pass can be factored into a first order all pass minus alpha 1 star plus z inverse plus z inverse divided by 1 minus alpha 1 z inverse. Both numerator and denominator has got a first order factor out. So, then this must be, well, let us call it as a n minus 1 of z, it is a one polynomial of one order less divided by b n minus 1 of z, one order less. If I call this as h n minus 1 of z, now h n minus 1 of z also is an all pass, because h n of z is an all pass. So, then this becomes an all pass of order n minus 1. So, all pass functions have got a very beautiful property. You can actually factor them into lower orders and preserve the all pass property, and it turns out that the stability part also can be preserved going into the factorization. So, again it's got some very, very interesting and powerful applications in the context of signal processing. Our goal is to sort of pick what we need and move forward. Okay, there are a couple of special cases which, just as an observation, you can write down. So the repeated process of factorization says the following, that h n of z can eventually be written into a scale factor beta, again that is not significant for us. The rest of it is a product of first order all pass functions, k equal to 1 through n, denominator is 1 minus alpha k z inverse, the numerator is minus alpha k conjugate plus z inverse. Okay, notice the paraconjugation structure comes in and works beautifully for us. Okay, so this is the general form, and of course beta cannot be 0, it's some constant scale factor. Now, an important observation on this structure, once you said that any all pass function can be factored in this form, if a particular alpha k happens to be 0, then what do you get? Is it still an all pass? Is that factor still an all pass? Yes, it's still an all pass. It is equal to z inverse. So, z inverse is actually a delay, it's an all pass function, and it it collapses to a delay. So, the case where you have all alpha k is equal to 0, all alpha k is equal to 0, then you get h n of z is equal to the scale factor times beta times z power minus n, that is fine. So, z power minus n is actually a special case. You can think of a delay as a special case of an all pass function. Okay, and hopefully that is useful and an interesting insight that you get from there. Now, before we leave the discussion of all pass, a couple of quick properties I would like you to verify or ascertain. Two properties which come to play in our discussion, properties of all pass filters. All pass filters belong to a unique category of signal processing functions which are called lossless functions. Okay, so lossless, the property of losslessness. Okay, what is that? What we say is, let us take h n e of j omega magnitude squared equal to 1. We have taken the constant equal to 1 for all value of omega. That is the definition of an all pass function. Now, if I feed in any signal x of n to this filter, all pass filter h of z, out comes y of n, then by Parseval's theorem, I know that the input output power relationship is given by 1 over 2 pi integral 0 to 2 pi or minus pi to pi mod y e of j omega magnitude squared d omega is equal to input 1 over, writing the Parseval's relationship, it is mod h e of j omega magnitude squared x e of j omega magnitude squared d omega. Right, that is input output relationship for LTI systems for using Parseval's, but this one is exactly equal to 1. So, therefore, the energy of y is equal to the energy of x, or if you write it in the time domain, this will be n equal to minus infinity to infinity mod y of n whole squared. On the right hand side we get n equal to minus infinity to infinity mod x of n whole squared. Energy is preserved. That is why it is called lossless function. Okay. The second part that second property that is very important, again I will state it without proof, but please do read up or look up. Again, the result is what is important for us. This is called the maximum modulus theorem, of analytic functions, for analytic functions, complex variable theory. Okay. Now, if h of z is a causal stable all pass, okay, causal stable, that means there is no powers of z, all the poles are inside the unit circle, causal stable all pass. Then one thing we know, mod h of z, h of z is mod h of z is equal to 1 on the unit circle. This is the unit circle. Okay. Next part is the non-intuitive part, requires proof, but I am stating it without result. Please do look up Vaidyanathan's book. This is less than 1 for mod z greater than 1, greater than 1 for mod z less than 1. Okay, that is using the maximum modulus theorem for analytic functions. This is a result that is derived. Now, I want to just do a sanity check. Where are the poles of h of z? Inside the unit circle. So, there will be points where the magnitude of h of z is going to blow up, which means it will be greater than 1. So, that satisfies. Inside the unit circle there will be poles which will cause it to blow up. So, basically it is not only at the poles, but everywhere inside the unit circle, because of analytic continuation it's got greater than. So, basically the maximum modulus occurs on the contour mod z equal to 1, or the minimum value. Okay. So, basically, and once you have proven that property, then everywhere outside has to satisfy the other constraint, which will be mod of h of z is less than 1. Okay, this again is a useful result, but the result is more important than the result so the last one I would like you to verify is something called the monotone property. I will write it down quickly, we will stop with that. Monotone phase property. Okay. So if I have a all pass function h of z, which is given by 1 plus a z inverse a conjugate plus z inverse, that is a first order stable all pass. Basically the I will say that mod a is less than 1, that is the location of the pole. And now if you were to write h e of j omega, argument of h e of j omega, and call that as phi of omega, and show that d phi of omega by d omega is always less than 0 provided mod a is less than 1. That means it is a stable all pass. If I look at the argument of this, it is a first order all pass, it is monotone decreasing, slope is always negative. Okay. Easier if you use the following convention, again you can show it, please do show it, it is not a difficult task, and in fact probably in DSP you have already done that. So please use the following notation, it helps. If a is equal to minus r e power j theta and r is less than 1, greater than or equal to 0, less than 1. So okay, we are using this notation, then you can show that you can write h e of j omega in the following way: e power minus j omega 1 plus a star e of j omega. Basically this is the notation where we do the use the paraconjugate, divided by 1 plus a e of j omega, and from this it is easy to show phi of omega is equal to minus omega plus tan inverse of r times sin omega minus theta. So basically we are writing r as a as r a e for j theta, this divided by r cosine omega minus theta minus 1. Okay. So please write down the expression, basically differentiate phi of omega and show that it is d phi of omega by d omega is less than 0 if r is greater than equal to 0, less than 1, which is that is under this condition you can show that. So this is monotone phase. So three properties of the all pass. One is the losslessness, we have proved. Maximum modulus we have stated without proof. Third one we have stated it with the request that you should prove it. Okay, thank you. We stop here and pick it up. Correct, correct, thank you. Yes, e power put it in the wrong place. Correct, thank you. We stop here. Okay, so please read sections 5.1, 5.2, 5.3, which gives us a good platform for us to complete our discussion on all pass functions. But we are going to now go into a discussion on the structural all pass properties. How do you derive a structure that will guarantee the all pass property even under quantization? Thank you.